Okay, now recording is up. So this part of the lecture should be relatively short compared to the first part and the last part, right? So we will go through what are the other way to handle branches before we move on to like predicated execution and superscalar. So if you don't want to do branch prediction, you can do other technique like delay branching or fine-grained multi-threading or predicated execution or multi-path execution. These are the options that some CPU, for example, give these to you on top of branch prediction as well, right? For example, the branch delay slot that looks like this. Like let's say you have a branch instruction. One thing you can do is remember you have the 5-stage pipeline, like fetch, decode, execute, memory, and write back, right? And we know that this and this is when we know the branch status, right? That's when we know the branch status. And that's basically, if you want to stall, you have to waste one cycle, right? You have to insert the bubble. So let's say branch is here. If you want to stall, this will be a bubble, right? So the concept behind branch delay slot is the compiler, not the hardware, the compiler. When you compile your program, it sneaks in independent instruction over here in the fetch. What does that really mean? It basically means that the compiler look ahead in your code and try to detect, are there any instruction that has nothing to do with my branch? It has nothing to do with my branch, and I fit it in that bubble. So instead of not doing anything, I run that one instruction that has nothing to do with my branch. So I can feed the code in and assume that I don't have any data dependency through branching, right? So that's the concept behind branch delay slot. And the way you detect these independent instruction is you can use compiler, right? You can write your assembly on your own as well. For unconditional branch, for example, the one that always jump, right? These are easy to fill in because you know how many cycle you have to fetch while you're in the delay slot. For the conditional branch, which means that you have to figure out if it's taken or not taken. This is harder to fill in because if it's taken, you might have to fill in a different number of bubbles compared to when you have to take the branch. So it's more dynamic, right? And the delay slot works like this. So let's say you have the code here, right? And then this is a branch. And then the code here, code number 1, and then the code number 2, right? Or 2. Right, and then down here you have something that has nothing to do with the branch. Again, code, right? But this one has nothing to do with the branch, right? So the delay slot works like this. It would convert your program into something like this. Again, code 1, right? And then you have the branch here. And then the red code will be moved here, so that you don't have to do branch prediction, because by the time you have to run code number 2, at this point, branch outcome is known. That's it. That's the concept behind the branch delay slot. You move code around so that by the time you need the result of the branch, you already know the outcome in the pipeline, so you can do data forwarding. Right. You can do fancy version with delay slot as well through a technique called squashing. Basically, if you have a slot instruction like this, for example, you have branch X, right? This is a normal execution. You go like this and then you stall here because you have the branch, right? Sometimes you cannot find anything to fill in, so you do no op. This is actually stall, right? You can do squashing in the sense that if you do branch X, basically this goes back here, right? So you can try to put instruction A right here in the delay slot. And if you're not taking the branch, you kill instruction A. So that's like a small optimization over this. That's one way you can handle branch without actually prediction, like without actually requiring any prediction. The other thing is we can do something else. This technique can be called fine-grained multi-threading, right? So because the hardware can maintain multiple threads on the go as well, when you have a branch instruction, you can switch to another hardware thread. We'll go into more detail when we talk about the GPU and we talk about multi-threading. So we are not going to dive into this concept right now. Basically, instead of waiting for the outcome of your branch, you do something else. You run a different program. You run a different thread. The downside, you have lower single thread performance and you need extra logic. Basically, it is more costly in terms of the hardware to implement this. And your program itself, your program that you run, your application has to be able to do multi-threading, right? Again, we'll talk about this concept when we further along in the GPU lecture and in the multi-core multi-threading, all right? The next thing is we can get rid of control flow. This is actually a common thing in x86 and ARM when you have a small if else. So let's say you have a if else that's like one line long, right? One line of code. And else here, one line of code, right? So basically it's a short if else statement. You can use predicated execution as well. The way predicated execution works is you change control dependence, so you don't wait for the outcome of your branch. You convert that to data dependency, because if you know about something from pipelining and data forwarding lecture, data dependency you don't have to stall. You don't have to stall. So example is in the ARM, right? Say you can use conditional register to check if I have to add some or subtract or not. It will do add or subtract depending on the outcome of my previous line. This also is available in x86. And this depends on the ISA definition, but it's, again, the general idea is called predicated execution. GPU also use predicated execution as well. The benefit is you instead of actually branching, right, you do something like this. Let's say you add, right, 0, 1, 2, and then you subtract, right, 3, 4, and 5. The predicated execution is something like this. Add only if the subtract is 0, 6, 7, and R8. This line will only add the two numbers together if my subtract result in 0. That's predicated execution. It's not branching. This is not branching at all. You either add or not add, depending on the result of my subtract, right? So now, this means that your instruction doesn't jump in control flow anymore. It's just some dependency check that you have to do. Do you have to do that add, or you just flush them away? You also the benefit is because you convert control flow into a big block of code without if else, compiler can further optimize that. Compiler love big block of nothing without if else. A big block of just compute instruction, compiler love that because it can do a lot of optimization on it. The downside is if the if else is a big giant chunk of instruction, then it requires a lot of useless work because you have to figure out, okay, do we add in a big block, right? So it should be done for just short and quick branches. So that's predicated execution, right? And now we are basically transitioning to the next concept. So we do a quick 5 minutes break in the middle, and now we'll resume with superscalar. All right, so let me stop the recording for part 2 of the lecture, and then we'll resume with part 3 when we talk about the CPU design. This will have more to do with how to get performance. It's not about branching anymore. So that's why we do a pause here. All right.